more of a Bayesian approach to parameter estimation, right. Right. So, I am going to say that there are two goals to us. We want to estimate the parameter values, right, that best explain some given data to us, right. We already looked at this in the context of logistic regression, right. So, we assumed some kind of a model that was generating the data, and then we estimated the parameters of the model that somehow best explains the data, right, and we used the notion of a likelihood, right. We are just going to look at it again little in detail, and then go on and look at a couple of other ways of doing parameter estimation. The second thing we look, second problem that we are interested in is essentially calculating the probability of new observations given the old training data. Right. So, I am going to assume that the parameters are given by theta, right, and the observation is given by capital X. Okay. So, what I am interested in is probability of theta given x, right. That is all familiar Bayes rule. So, what is that? What is that? Huh? Prior.
Evidence.
Posterior.
Likelihood.
Likelihood.
Okay. Huh? Likelihood, right. So, we already looked at it. So, right. So, I am going to write the likelihood as likelihood of theta given x, right. So, if I write it like that, people get a little confused. It is the likelihood of the data, right. I already mentioned this is the likelihood of theta, not data. It is likelihood of the parameters given the data, even though we write it as probability of x given theta. Is it clear? Why is it a function of theta not of x? Because x is fixed. In our context x is fixed, right. I have given the observation x, right. I am interested in finding the parameter values theta. So, the way I am going to set this up for a given x, okay, for different thetas, what is the probability of that x? Right. Let us say I can consider 5 different thetas. For theta 1 what is the probability of x, for theta 2 what is the probability of x, for theta 3 what is the probability of x, and so on and so forth. So, that gives me the likelihood of theta. Okay. Sometimes people say the likelihood of x with respect to theta. In fact, it's so widely used, I don't know if it is even right to say it's incorrect anymore, like prepone a meeting, right. So why are we interested in the likelihood? Why are we interested in the likelihood? Sorry?
Changing that theta value is useful.
Yeah. So what I am really interested in is to find that theta that best describes the data, right. So essentially what I am interested in is finding the theta that has the maximum probability here, right. Given the x, which theta has the maximum probability, right. So x is fixed, right. So this does not matter, and if I really do not have any information about what theta is the best theta to start off with, right, this is also irrelevant because it will be the same for all the theta, correct. So if I want to maximize p of theta given x, all I need to do is maximize p of x given theta, because this is constant, that will also be constant across all theta, right. So it is enough if I look at the likelihood, right. So if I make an assumption that all my data samples are generated independently, right, I might as well write my likelihood as a product of the individual probabilities, okay. When we do not want product of probability, so we typically end up using the okay. People agree with that? Right. So suppose the new data point x tilde comes, what is the probability of x tilde with respect to x, I mean given x, sorry, given that I have already been given some training data x, okay, I am asking you what is the probability of this new point x tilde, so what will be the probability? Right. In fact, this is exactly what we did in the logistic regression case. We found the maximum likelihood parameters for the for beta, maximum likelihood estimates for the parameters beta, and then we plug them back in and said, okay, this is how you estimate the parameters. Okay. Right. So let us look at a simple example. Let's consider the simple coin tossing experiment, right. So there is a random variable c, okay, which has some outcome lowercase c, right. So lowercase c, if it is 1 it is heads, if it is 0 it is tails, okay. And what is the parameter that I have in coin tossing experiments? Probability of coming up heads, okay. Let's change the symbol, okay, still looks like p but it is a row, okay. So the probability of whether you come up with heads or tails, right, given the parameter rho, okay. So what is the probability? That should also look familiar, we already saw that, right, in the context of class label being 1 and class label being 0, right, and the probability of coming up class 1 versus probability of coming up class 0, right, it's like heads and tails now, right. The probability of coming up heads, well, rho power c is the, well, if it's 1 then it is rho, if it is 0 which is tails it's 1 minus rho, okay. So this is the expression in simplified form, otherwise I would have written, I would have to write it as rho if c equal to 1, 1 minus rho if c equal to 0, right. Instead of that I can write this using a selection function like that, okay. So what is this probability density called? Bernoulli, yeah, okay. The Bernoulli density. So what's the likelihood going to look like? For each of the ith toss you would have one outcome lowercase ci, right. So what is the probability that the random variable can be lowercase ci given the parameter rho, right, and sum this over all the right. So there are n1 times heads has occurred, let us say, and n0 times tails has occurred, right. Then I can simplify this summation as n1 times log rho plus n0 times log 1 minus rho, right, it's simple enough. Now take the derivative of the likelihood equated to 0 and tell me what rho is. Right. So our common sense way of estimating probabilities from experiments is what? Toss a coin n times, find out number of times it turned up heads, okay, divide by n, that gives you the probability of it coming up heads, and turns out that is the maximum likelihood estimate assuming that your coins is obeying a Bernoulli distribution.